Earth Science, welcome back. Today we are going to be talking about Chapter 8, which is Plate Tectonics, and this is talking about this moving, changing Earth. Remember that the Earth is not a stagnant object, it is something that is constantly changing, it is building, tearing down, things are being created and destroyed all the time. So to start off, we have to talk about a little history. What is plate tectonics? And if you remember from our discussion about the Earth's kind of structure, the crust of the Earth is called the lithosphere. And this lithosphere is broken into several different plates that move on the molten surface of what we call the asthenosphere, that upper layer of the mantle, lower layer of the crust. Plate tectonics is this theory that describes the formation, interaction, and movement of these plates as they move across Earth's surface. So some early evidence for this: in the early 1500s, explorers were mapping both South America and Africa, looking for spices and trade routes, and etc. They noticed that when these maps were placed together, if you cut out all the ocean in the middle, they look like they kind of fit together like a puzzle piece. And in 1596, at the end of the century, a Dutch mapmaker suggested that the two continents at one point in time had broken apart. Alfred Wegener suggested the hypothesis of continental drifts, that the continents are drifting apart from each other. And his quote from him is, "The continents have drifted over time," meaning they have moved from their original position to something different. So some evidence for this: many of the continents' shape, as we got better and better maps, seem to match up. And furthermore, a fossil of a reptile called Mesosaurus that lived 270 million years ago could be found in both South America and Africa. So it made sense that this small reptile that was found in both areas, at one point in time, it was living on this continent that was together. They also looked at the strata of rock, and they seen that specific rock formations would line up if those continents were together. So here's Mesosaurus, the fossil, on the left here, and here's what we think Mesosaurus. Here's the kind of artist's rendition of what we think it looked like on the right. These were found in both South America and Africa, kind of pointing towards this hypothesis that these continents had drifted apart and that at one point in time they had been one continent together. There were some objections to Wegener's hypothesis. It wasn't super popular at the time. It was, and the kind of like backlash was not that the continents have moved, but how have the continents moved? Wagner at the time postulated that continents might float on deeper, more fluid layers beneath them, and he was very, very adamant in defending this hypothesis and defended it his entire life. He truly believed that continental drift was the explanation for these continents' shape and their position on the planet. But he was not successful in his lifetime, anyway, of moving the scientific community towards this idea of continental drift. Out of kind of newer information and moving towards a better understanding of the subject, we devised the theory of plate tectonics. There was lots of discoveries about earthquakes, magnetism, the age of rocks, and the age of rocks on the ocean floor that pointed towards this idea of continental drift, but not in the way that Wegener suggested. Wegener had suggested just the continents were moving on this liquid layer. This new evidence pointed in a different direction. This new theory, this plate tectonics, is that the continents are embedded in larger lithospheric plates. As these plates move, so do the continents on them. Now, what's different than Wegener's theory is the oceanic basins and oceanic parts are also on these big lithospheric plates. The oceans are also moving, not just the continents. So, the locations of earthquakes and volcanoes in this evidence for continental drift and plate tectonics was the locations of earthquakes and volcanoes are not random. They are concentrated in these heavy belts across the globe. These belts, we now know, mark the boundaries between plates, where the two plates are meeting, where they're pulling away from each other, or where they're sliding past one another, as is the case in the San Andreas Fault over in California. Another piece of evidence was magnetism. Igneous rocks contain minerals that are magnetic. This is a lot due to the nature that a lot of magma has iron inside of it. These rocks hold a record of the Earth's magnetic field. As the Earth's magnetic field reversed, we could see in these rocks this difference of reversal. So in one layer of rock, maybe the North Pole was where it is today, pointing traditionally up when we draw it, and in another layer of rock, the North Pole was now pointing downward, as if the South Pole had been the North Pole for that period of time. And this showed us that the poles are not stable. They shift occasionally. Another piece of evidence is these mid-ocean ridges. These are long chains of volcanic mountains on the ocean floor. They have a deep central valley. As these ridges are kind of splitting and going their own way, this new seafloor is being created. These new volcanoes are forming throughout this ridge. So as we push this more magma up, it is pushing these rocks out, making more rocks. And rocks on either side of this showed these same reversals that we were seeing before, where if this is a different layer, this layer is pointing up, and this layer is pointing down. So there are three types of plate boundaries. There's three kinds of ways that these plates will interact with each other. And there's three big categories, and then there's a couple little sub things underneath a couple of them. So the first one is divergent. And in divergent boundaries, we're going to talk about these in a little bit. These are going away from each other in some manner. Convergent boundaries, our second one, these are plates coming together in some kind of fashion. And then transform are when they are sliding past one another, kind of like that. So the first one, divergent boundaries, these are when two plates are splitting apart. These are mostly occurring on the ocean floor, and they form these rift valleys, these very deep valleys, these mid-ocean ridges at the center of a mid-ocean ridge. So mid-ocean ridge is all of these volcanoes that are being formed there. The Rift Valley is this very deep spot there that's formed in the middle. And this is new oceanic floor on either side, moving away from each other. When we talk about a rift is a crack in the ocean floor where molten rock forces its way upward. These rifts, especially along the mid-ocean ridge, will kind of move like this and create new sheets of rock on either side. And this is how we get seafloor spreading, the process of molten rock forming new rocks at these rifts. And this is why a lot of the ocean floor is a lot newer than the continental kind of material, because it is this older kind of process, this new process of these new rocks being formed. All right, convergent boundaries. These are the ones that are coming together and colliding. There's two different types of these convergent classifications. There's subduction, where one is going underneath of another, and there's collision, where these two are crashing into each other and butting heads, as it were, making a full collision like two cars coming together. So in subduction boundaries, this is what happens when one is plunging underneath the other one. As this happens, this is always going to be an oceanic plate being subducted. Oceanic plates are denser, so they're going to go underneath of another one. Let's say, for example, we have this nice continental plate sitting here. This oceanic one is going to push its way underneath, back down into this boiling hot magma down here. At this place where they meet, we're going to call this a deep sea trench. And these are even more common when we have two oceanic plates coming together and the oceanic one is being subducted under another oceanic one. This is like things where the Marianas Trench is being formed, where this here is this really, really deep area that's going really, really close to the mantle underneath of it. So the locations for these, they can form between ocean-ocean plates or between ocean and continental plates. They also are usually followed by the formation of volcanic islands, like Hawaii and the Philippines. In this kind of the Philippines example, where we have this ocean plate being subducted underneath another one, there's going to be plumes of magma coming up here as this material gets melted and forms these nice volcanoes. that are usually under the ocean, and as they get bigger and bigger, they will reach to above the ocean and be their own little volcanic islands. So which plate gets subducted? And we kind of alluded to this earlier. It's always, always, always going to be the oceanic plate. This oceanic plate is always going to get subducted. So if it's in between an ocean and a continental, the oceanic will go underneath, the continental will go on top. This is because the oceanic plate is denser. And as it starts to get pulled under there, this section here is going to be exerting kind of this pull on the rest of it down into there. Where this is happening, we get these really, really big mountain chains that you can see here. So this is nice mountain arc here in this volcano. This is this kind of being pushed up by this subduction here. All right, in collisions, these are when two big continents are coming together. They will get welded into a single larger continent. Usually this is when we get two continental plates coming together. This will cause, as these two run together, they will cause these really big mountain chains at this place of convergence. This is how we formed our tallest mountains, the Himalayas, which contain Mount Everest, the tallest mountain on Earth. This is how it was formed, as these two plates were colliding, pushing these big masses of rock up to create these really, really, really tall mountains. All right, transform boundaries. This is our third type of boundary. This is happening when two plates are moving past each other. So one's moving kind of up and down here, and the other one's moving side to side. This would be on the planet. It would be like east and west or north and south. They're moving each of the other direction. And this is an example of, this would be the San Andreas Fault, which is a transform boundary. And these boundaries, when we talk about earthquakes, are really, really high prevalence of earthquakes. There's a lot of earthquake activity along these boundaries. It's a lot of friction here as these two are rubbing together. There's a lot of things going on there. All right, so causes of plate movement. There's kind of three main theories or three main parts to plate movement. We don't think any one of them is responsible. We think it's kind of a combination of all three. And the three are mantle convection, ridge push, and slab pull. In mantle convection, this is the transfer of heat from the Earth's core to the mantle. The core is a lot denser. There's a lot more things rubbing against each other, causing this friction. As it heats up the mantle, this mantle will rise, hit that colder crust, and then circle around, drop down again. Think of this as like the water boiling in your teapot or kettle on the stove. That hot water rises, cools against this cold continent, and then falls back down. As it cools, it gets heavier and denser and will sink down further until it hits this core again, and then we'll go back up. The problem with this theory is there's not enough power here. It's not compressed enough for there to be enough power for this to truly be the only driving force. That's why we have to have things like ridge push and slab pull that also help along with this. And ridge push is as this magma is rising, it heats the rocks around it. These hot rocks at the beginning of this kind of area are very, very elevated. They're very less dense because they have more air in them. So they're more buoyant than these rocks down here. They will float kind of higher than what was made before. As these new rocks age, they also start to cool. And so now we have these cooler rocks, which are now denser. Denser things get pulled by gravity harder, so they're getting pulled away from this rift, so that new magma can come up here and form a new lighter kind of chunk here, that as it cools will move this way, cool down, and start to sink again. Although this is called ridge pushing and the ridge pushing theory, gravity sliding is a much better name, because as these things cool down, gravity affects them more. They slide down this kind of slope here, and then allow more magma to come up behind them and fill in that space. All right, slab pull. This is at subduction boundaries. We have these kind of heavier plates. These ones get dragged beneath the other one. They are denser. This edge of the plate here initially is colder and denser, so it starts to go down. As it does, it pulls the rest of this plate down with it. This is called slab force. This is the force of this gravity pulling this huge chunk of ocean, usually, down towards the core. As this gets down in here, it heats back up, melts. It's still pretty cold, so it'll join this kind of downward force, and then through mantle convection, come back up towards this ridge. So this is how these three kind of theories are all working together here. So using kind of these plates and these rocks and the magnetism record and the age of fossils, we can reconstruct the past. We can see things like the Appalachian Mountains, or these mountains that are formed from tectonic activity, but they're no longer on a plate boundary. There's no active plate on the east coast of the United States. Geologists can use the age of rocks to help to reconstruct Earth's past and see what it looked like as these tectonic things were going on. So the main theory, and there are continents before Pangaea, but at one point in time, all of the continents came together to form Pangaea. And we can use the ocean floor to kind of see these newer areas of floor that have formed after the continents split. And the main theory is that Pangaea was formed as these two smaller land masses were smashing into each other. The first was Gondwana, and the Gondwana was this larger continental mass, and it was kind of in between the South Pole and the equator, and it would eventually become the continents that are Africa and South America and Australia and Antarctica, and there's also India on here and Madagascar. As this moved north towards the equator, going this way, if north's up here, it would collapse. It would collide with a smaller mass of land. This smaller land was called Laurasia. And Laurasia, this one up here, eventually Pangaea would break up, as all couples do, Laurasia and Gondwana here, and these two would split and continue to split into the different continents we see today. So North America and Greenland and Iceland and Europe and Asia are all on here. Gondwana has Africa and South America, Madagascar, Australia, all these other continents on it. Now, the continents are much bigger than they used to be. And how does this happen? How do we get more continent? Well, rock is added on the outside of the continents due to these tectonic activities. So the thing we should first start on is what was the original continents? And that this oldest part of a continent is called a craton. These are the oldest deposits of rock that are found on that continent. For the North American continent, our craton is in eastern Canada. Everything else is newer. It's called the Canadian Shield, and it's almost 4 billion years old, 3.96 billion years old. Very old structure. So where do we get this new growth material? Well, the first is from deep sea sediments, and these are added to the outside edges of continents at subduction boundaries. As this oceanic plate is going underneath the continental one, some of the sediment gets scraped off, and it forms this new shelf on this continent, on the continental plate. The second is igneous rock. We get things like plutons, where this magma is forcing its way underground and cooling and hardening, which gives us a whole new, mountain like building material. It gives us all this new material for building land. We also have volcanoes that eject brand new material right onto the continent as lava, ash, and rock. We also have volcanic islands that form, and as these continents and plates move and drift, these islands will run into another continent, and they will get added to that continent's mass. The third is river sediments. We have a lot of sediment on top of mountains, on top of hills, and across the plains. As rivers move across these structures, they break down parts of these mountains and carry them with them. When they get to the ocean at the edge of the continent, they're going to deposit these sediments at the continent edge, making a little bit more real estate very slowly. And the fourth is terrains. And terrains are large chunks of lithospheric plate that has moved and attached to the edge of a continent. And all continents, and to be a continent, you have to possess some terrains. And how do I determine a terrain? Well, you identify a terrain, it has to have these three things. It has to be bounded by all sides by major faults. Basically, it has to be an island. Let's say I have a chunk here, and my terrain, let's use purple. I haven't used purple this presentation. My terrain here is kind of inside of this larger continent here. But all the way around it here are these very active faults. The rocks and fossils of the nearby rock don't match. This one might have quartz, and this one might be clays and silts. And the magnetic record doesn't match. Maybe this nearby rock says at a certain depth it was going towards the South Pole was the North Pole. And this one says, no, it was the North Pole at that time. This tells us that the age of these rocks doesn't exactly match, and that this piece of rock is not from around here. That concludes our chapter on plate tectonics. I hope you learned something. I hope you enjoyed it. Let me know if you have any questions. Have a good rest of your day.